All right, I want to talk to you today about language-oriented programming. Some of you, I don't know, this is an old term, but maybe not everybody's heard about it. It sort of exists in the same space that object-oriented programming exists. So when you're thinking about building a system with object-oriented design, you think about the relationships between your objects and your methods, and what messages objects can receive, what relationships they have. Language-oriented programming sits kind of in the same space, but instead of thinking about objects as a way to decompose your system, you think, what programming language would be the best one to implement this? And then you factor your task into implementing that programming language and then implementing the program in it to actually build your system. So you've probably noticed these things animating on my slides here. So what I want to show you is the programming language the programs that are running there. It's a Lindenmayer programming language. And have you encountered Lindenmayer systems before? Yeah, okay. So a Lindenmayer program here consists of three parts. You get an axiom, which is a sequence of symbols, and you get rules that rewrite the symbols. Okay? So here we start with the symbol A, and the rules A rewrites to AB, and B rewrites to A. Let's start with this one. Sorry about that. And then you have a series of variables. In this case, we have only n equals 4, which tells us we're going to run this program for 4 steps. And so we get this A, B, A, B, A out. Does that make sense to everybody? So like if we ran for 1 step, we'd get A, B, and 2 steps, we'd get A, B, A. So they're always rewriting in parallel. Every single symbol is rewriting according to one of the rules at every single step. This was one of the very first Lindenmayer systems, and it was used to model algae. And the idea is that A is an adult algae, and B is a juvenile. And the first rule represents asexual reproduction, and the second one represents becoming an adult. One interesting fact about this Lindenmayer system is that the ratio of A's to B's approaches the golden mean as you run more and more generations of these. And so our programming language gives us a way, which is what I had open accidentally at the start, to extract some value out of the sequence that you ran, the sequence that the Lindenmayer system computed. Hashlang Lindenmayer at the top here tells us that we're in the Lindenmayer language, and then this thing here, typed Racket, a language name that follows it, tells us that we should expect a series of equal signs, and then what follows the equal sign should be a program in that other language, which is then going to be used to extract the value from the result of the Lindenmayer system. So you have to define a function start, which gives you some initial value, and then you have to define a function for each of the symbols that will be in that string, and those just get called in order with the initial value that then produce new values. And so you see what happens here is we start out with a pair of 0 and 0, and then if we encounter an A, we add 1 to the car position but leave the cdr alone, and the opposite for B, so we're just tracking the number of A's and B's. And then at the end, we take the ratio between them, and if I run this program, we get some debugging code, because I was fixing a bug in Dr. Racket last night. And an approximation to the golden mean. OK, so yeah, please ignore the purple. You don't have to have written this in typed Racket. We could have written it in Algol 60. And so you get the same thing back. So it doesn't really matter if we, let's see. So you can run it for 30 generations, and you get some slightly better approximation to the golden mean. Okay, so Lindenmayer systems were, designed to explore biology. Botany seemed to be used a lot in them. And the symbols come with standard interpretations in turtle graphics. So F represents moving the turtle forward, and plus and minus turn the turtle. And so if we were to run this one, we get this nice picture. So you can see after 1 generation, that single F there turned into that particular sequence of turns. And then we can turn each of those Fs into that same sequence, and you start to, okay, you get the idea there. And then, okay, one more feature of the Lindenmayer language, so I can show you an actual plant, is that the symbols can come with parameters. So here, these parentheses are not symbols. What they mean is that that's a value that's associated with that symbol. So this is the symbol A, and it has initially a value 1. And the rewrite rule can then take into account what the current value is, S, and then we'll rewrite it into this sequence of symbols. So you've seen f plus minus, and a is of course defined there. Bang changes the width of the line that the turtle's drawing, and open square bracket is a symbol, just on its own, and its interpretation in the turtle land is remember the position of the turtle, and then when you meet the matching closed square bracket, leave the lines as they were, but put the turtle back where it was at that moment. Okay, so if we run this one.
What are minus 5 and plus 1?
Minus is either turn left or right, and plus is turn right or left, and the 5 and the 1 control how much it turns. So all of these things, like f takes a parameter, and if you didn't give it a parameter, it'll just move a certain amount forward. But if you give it a parameter, that parameter will control how much it moves forward. So they all work like that. So here, this is what you get. Let's move that over a little. And we can adjust the parameters like I was doing earlier with n, but we could do it with theta, sorry. We could, like, if you make theta 20, you get some kind of non-tree-like thing coming out of it. So that's how all those pictures were being made on the side of the slide, is I was just making much less violent changes to the parameters over time and showing you what kind of looks like plant growth up here. Okay? All right, so there's an immediate problem that I hope comes to mind. When you look at these Lindenmayer programs, you probably think to yourself, like, that's really almost the same as OCaml code anyway, right? I mean, I could have written a append map or something, and what's the problem here? Why do I need a whole programming language for that? Which, of course, is the way I would say this is, we have a programming language, my favorite one. Why can't I reuse that one to implement? What does it mean to reuse that one to implement the Lindenmayer language? I mean, the Lindenmayer language has a long history, longer than OCaml, as it turns out, or Racket, for that matter. So is there a way that we can take these languages that we have and reuse them to be able to still write computations the way the Lindenmayer community has been writing them, and run them and explore them in this context? All right, so let's think a little bit about the high-level structure of a programming language implementation, right? You can sort of divide into two pieces: the code that's around when the program runs, and the code that translates the program in Lindenmayer language to x86 code, say, which is what was happening there. I think we understand relatively well how the runtime system we can get reuse. I mean, there's still a lot of work to understand reuse in general, but let's say that's functions and data structures, and we have a much better handle on that than we do on how we might reuse a compiler. So let's open the box a little bit. Inside, you have a compiler. It's like a function that gets in a tree in some syntax, and then does a case dispatch on what kind of thing it is, and then produces some new code. Okay. And you can reuse that in the sense that you can supply different inputs to the compiler, different programs, and get different programs out, and there's lots of reuse along those lines. But this is a very granular form of reuse. And what we might wish to do is, instead of think of this as one giant box, but think of each of these as the individual boxes that we can put together and rearrange and compose, and maybe build 4 different programming languages where I've kept most of the same parts of that original programming language, but I've dropped some things, or I've changed how the compilation works in a few cases. Okay, so you could probably imagine, and if you could implement your own DSL that would support this kind of reuse of a compiler. So I want to take things one step further, because I think there's an important extra step that I'm going to use these 3 words to describe, where what we really want to think about is being able to take the compiler and in each scope adjust the set of cases that we have available. Okay, so it's a little bit strange. There's one word on the next slide. The first person who can tell me what that word is, I'll buy a cup of coffee. Yeah, okay. Catch me later. Yay. Okay, so what I want to show you now is, here, let's go back to Lindenmayer systems. This parameterized non-terminal, it has a notion of arity. Okay? And so if we were to change its arity, so down here, if I say comma t, well, this is going to be a syntax error now, because it's going to say that these two don't match up with each other. The use of a up here has only one argument, but you've made a declaration that has 2 arguments, or parameters really, and is what we want to think of parameters non-terminal. So if I put 2 parameters everywhere, now oops, it compiles again. You get this little green thing here, and I get my arrows back, and all that good stuff happens. So what we really, these regular old functions in Racket are not a good target. They're very close to a good target, but they're not quite the right target for parameterized the parameterized symbols with the rewrite rules here in our Lindenmayer language because they don't have this like compile time checking of the arity. Because of course they aren't, because they're higher order functions. I mean, that doesn't make sense in a higher order setting. But they're never higher order symbols here. So what we might want is a different target. Okay, so let's take a little bit simpler example. Here's a program that has an arity error in it, which you can probably spot there. I meant to call fyz once f, and then I meant to like just stick x in, but you know I'm thinking twos, and so I put x and y in there, and oh, okay, that's a mistake, right? So if we had a construct called define arity, then this would be a syntax error, this program, because the use of f on line 4 there has 3 arguments. But the use of line f on 5 is okay. So that's what we're aiming for. I want to show you how you can extend the compiler using a kind of scope-sensitive notion in order to get to define this construct, define arity, and then mostly reuse function definitions in Racket. Okay. All right, so that's too much to do in one step. So instead, we'll define a counting application. Okay, and bear with me on why this is a useful step. But what we got is a new piece of syntax called a counting application, which is like a regular function application, except instead of supplying just the function, you also put a number there that's the arity of the function. Okay, so this is a weird little new construct, and I'm showing it to you because I can introduce how macros work in Racket first, and then once we have that, we can take the step to define arity. Okay, so I factor this into like teaching you a little bit about syntax in Racket first. Okay, does everybody get this? So the first line 4 there, f gets 2 arguments, but there's 3 sub-expressions, so that'll be a syntax error. And on line 5, f gets 2 arguments, y and z, and that matches the 2, so that won't be a syntax error. All right, so here's the implementation. Let's go through this. So on line 0, up there, we say define syntax CApp, and what that means is we're introducing a new form, the counting application form, and we're writing it as a function. So this will be a function that's called at compile time by the compiler whenever it encounters a counting application form. Okay, and the argument, stx there, that's named stx, that argument will be a tree that will be the representation of the entire counting application form. So like, counting application f, x, or f2, y, z, it'll have 5 subtrees in it. So it'll have the identifier, which is the counting application itself, and then we'll have the f, and then we'll have the 2, okay? All right, and then we use something called, there on line 1, syntax parse is like a pattern matching form for matching on these kinds of trees. It's a fantastic little DSL in its own right that I'm using in a very simple way here. So we say like match, basically, and then here's the pattern that we're gonna match. So we expect an f and an n and some number of arguments, and ellipses is part of the pattern language. It means as many as you want of the previous thing. So args won't be just one subtree, it'll be a sequence of subtrees. Okay. And then we'll call this function verify arity. And verify arity will return or it won't. It won't return, it'll raise an exception in the case that the arity doesn't match, and it will return if the arity does match. So assuming it returns, then the result of the counting application macro will be this piece of syntax, which is the function applied to the arguments. Okay?
What's the hash quote with?
Hash quote means this is my convenient notation for building a new tree. So if I just put f args, that would be a call to f, but there is no f in scope here. That'd be a weird error. But hash quote f means I'm building a tree now that consists of an application of f to arguments. Right? Because we're running at compile time, the input is this tree, and we're building new trees out of the old trees, and okay. So it's a very convenient notation. Yeah. And you won't be surprised to learn hash commas coming in a moment. Okay, so begin for syntax. In Racket, you have to say clearly whether you're defining a function at runtime, or you're defining a function at compile time, or at the compile time of a compile time, which is like where syntax parse is calling functions. So begin for syntax means go one level up, and the things inside will now be functions that we can call at compile time, which is what we want. We want to be able to call this verify arity function. So here's verify arity. It just takes those arguments. It's just a regular function now. We're just computing at compile time. So we're going to count the number of arguments that we have. Syntax -e means given a tree, give me the piece inside the tree. So give me, if I have a leaf node, that is a piece of syntax that it contains a 2 inside, say, for example, syntax E will give you the actual 2 out of the tree. So it'll just remove all the metadata information there, like what line number was this 2 on, and things like that, and give you back the actual 2. Okay, so another, just to make sure it's clear what's going on, if I had written weird syntax in counting application, I hadn't put a number in that spot, this would just like crash. Compile time error involving equals, so it'd be a bug in my implementation of the define arity. All right, so if they don't match, then we call this nice function raise syntax error, which like puts together, builds an exception record and raises an exception that contains all nice information that lets my IDE know what the source locations are and lets me jump around or whatever. So that's one thing that actually raises the error. Okay, so that's the implementation of counting application. Does that make sense to people generally? Okay. We extended the compiler. We just added a new case to the compiler. Okay, there it is, define syntax. All right, so here's the trick. One little trick. We're going to expand define arity into a macro definition for f. Okay? And that's what's going to let us adjust how the compiler behaves in different scopes. So let's look at this a little bit more carefully. So we had that same function at the top there, and I will define real f to be the actual function that's going to be called at the when if we're allowed to make a call to what the original programmer thought of as f, there will actually be a call to real f in the program, and if not, well, the compiler would have aborted with a runtime error. So what's the macro going to do? Well, the macro just uses counting application. It counts the x and the y, gets 2, and then define arity turns into a macro definition of f with a 2 in just the right place. So f is now a macro that becomes a counting application. All right, here's the implementation of define arity. So this hash quote now is over a big range stuff. So we have the same first 3 lines that we had before, a slightly more involved pattern because we know that define arity expects, you got to put a function header thing at the beginning there. So we pattern match out a little bit more. And then at the compile time of define arity, we count the number of arguments that we had and bind that to n. Then the result of define arity is this big blob of code, which has the definition of real f in it, just sort of copied down, but given a new name, real f. And then there's a hash comma n. So we just drop a 2 right into the right spot. And now uses of f are going to be counting applications, which then call the actual f once the check has been done. And I made a helper function because it didn't quite fit on a slide, but this is the definition. This is just a regular function running at compile time to. Okay, so if you want to look at the code later, I'll make the slides available. But maybe you get the idea. The essential idea is that we can define arity itself turns into a binding which does more rewriting at the use site. So we can communicate across scopes, exploiting the fact that our compiler somehow understands scope in a very deep level, and we can use that to communicate across. It's like got a built-in accumulator for us, if that's one way you want to think about the compiler as a giant recursive function, but works with scope. Okay, so let's pull back out from that kind of deep technical stuff. This is a timeline of what I consider to be the most important macro papers. So to date, this was 1960. It's like basically hash define P4, the thing that we all enjoy debugging, because who doesn't love debugging? In 1963, it's not scope sensitive, but we got something where there were trees in our macro system. 63, okay? Already better than what we struggle with in hash define. It's integrated with the compiler and it has trees, okay? This paper, and I won't mention any others besides this one, 25 years ago, that's when we got the technology to make define arity work. Okay, and there's been some other cool stuff since then. So macros there's a lot of really deep thinking that's gone into macro systems, and you see it takes a while to like take the next step in these things. All right, so I'll leave you with 2 thoughts. This idea of using scope itself as a composition mechanism is kind of a weird combination of rules, but it's a very powerful idea that you can be able to define and extend your languages this way. And I think Racket gives you a platform for exploring the ideas of language-oriented programming, but there's a tremendous number of other things that we still have to answer as a community to be able to understand and do a better job with language-oriented programming. And I've just put some words and question marks there that sort of cover entire vast numbers of questions in each bullet there. Thanks.